All right, let's begin. So today we'll cover 18.3 and 18.4. Tomorrow, the second half, or the last bit of 18.4, and we'll start chapter 19. Food systems talk is at 4:10 tomorrow in here, the last of the three candidates. This guy, what did I know? His last name is Wood, and he's at the Yale School of Forestry, so I think that's sort of funny. It's not really funny, but it's sort of funny. He's talking, he's done work in West Africa. I think he's done work on soil structure in Senegal. I'm not sure exactly what he's talking about. But, homework up before the talk, 3 to 4, Thursday. Oh, there's also, I have to write it down. So Thursday also, 9 to 10. Corey, are you doing homework up this week?
I don't know yet.
Okay.
I'll look, no. Maybe Wednesday evening,
Yeah,
maybe not.
senior project time.
Yeah.
Friday we'll move into 19, chapter 19.1 and 19.2, homework help, usual time in the afternoon. Questions on any of this? Okay. So today we'll do 18.3, 18.4, and I'm never sure how things will turn out, but I suspect I'm going to do a little bit more talking than usual today. So that could be good news or bad news. You know, you tell me what you view this as good news or bad news. But it's a little, there's a bit more theory to explain, and the calculations are not that difficult that you need to practice tons of them. So the first stretch of long talking is likely about to begin. I mean, long might be like 15 or 20 minutes or something, so it's not going to be like, hey, here's the thing, do 10 of them. It's more going to be like, let me explain some stuff. So here's some stuff to explain. So what I want to start with is I want to remind you what we did last time. It seems like a long time ago, maybe because I did so many assignments over the weekend. So it seems like a long weekend. So we've been looking at line integrals. And so the picture here is we have a vector field F that's a bunch of arrows in space. You can think of it as a velocity field or flowing water or electric field. And we step along some curve C, and we take a little step, and every little step we take a dot product of the field. And this kind of tells us, on average, is the field helping us? Is it pushing us along? Or is it preventing us from going? Is the wind at our back or in our face? And we add up all those little bits, and we get this total thing. And then we saw to actually evaluate these things, we need to parameterize the curve. And so we write the x and y coordinates of the curve as functions of t. And t goes from a to b. We're often using 0 to 1, sometimes 0 to 2. And then we can express this way. And this looks like a bit of a mess, and it is for a moment. But this converts a calculus 3 integral to a calculus 2 integral. This is just an integral of a single, of a scalar, t. And so you do this dot product, and you get some function of t, and you integrate it, and you get an answer. And then you say, ah, that makes sense, or that makes no sense at all, but hopefully it makes sense. And my hope is this process, or my sense is this process seemed a tiny bit tedious. The hard part usually is coming up with the parameterization of the curve. Once you have this figured out, then you can just put your head down and do the math stuff you know how to do, take the dot product, do the algebra, do the calculus, get a number. Is that a relatively fair summary? And you might wonder also, is there some slightly better way to do this? Bless you. And the answer is yes, sometimes. And that's what today's class is about. So what I want to do first is take a step back to Calculus 2 and remind you of the fundamental theorem of calculus. And it says the following: t dt equals f of b minus f of a. So if you have an integral to do, you're like, oh, that's a pain. I don't really like doing integrals. Or maybe you do, but it still could be a pain. It takes some time. But if you happen to know that the thing you're integrating is a derivative of something else, then the integral is super easy to do. You just subtract this thing, and that's pretty nice. And if we think of this maybe as a velocity, and this as a delta t, then we can see we have velocities times time. Those will be a whole bunch of distances. So this is so we add up all the velocity times time, and that gives us the total. Well, these are all like little distances. In our calc 2, this was how far the cat ran all the time, and that gives us the total change in position. And one of the things maybe I want to suggest about this is, like a lot of things in math, this hovers on right on the edge between being incredibly deep and also obvious. So like this is sort of an amazing thing, right? This we define with Riemann sums. It's an enormous pain. It's really gross, right? We have to do all those Riemann sums. But then sometimes you can just subtract two functions. And this also says that all this stuff that's happening in here, all this addition in between A and B, is actually just sort of a function of the endpoints. So that's pretty slick too. So that's sort of deep and amazing. On the other hand, well, if you add up all the little distances the cat went, you get the total distance the cat went. It seems not profound at all. And so I think sometimes in math, like the idea here is that like this construction of the integral, the construction of the derivative, is exactly the right tool that lets you calculate things in an easy way. Anyway, so I hope this is sort of like both deep and obvious at the same time, if that's possible. Anyway, that's sort of how I think of a lot of good math has that quality. All right. So what I want to do now is think about this a little bit. And I think I'm going to do that over here, and then I'm going to put something else over here that's very similar to that. Just there's a reason, method to my forward irregularity. All right. So let's think about this. And we've got some function f of xy. This is some surface. And maybe I'm here at R1 and I'm here at R2. So these are two position vectors. And then this is going to be a delta r. And so I want to think about f R2 minus f of R1. So these are position vectors on a plane, and then we have some surface or some concentration or some rapid density here, and I want to know what's the change in whatever this function is when I go from this point to that point. Okay, so what's the difference between these? Well, you can think of this, it's the rate of change of f in the u direction times the distance moved in the u direction. So that's sort of, right, that's kind of going to be similar to this. We've got a rate of change times the time gives us the change. We've got a rate of change times, in this case, the distance gives us the change. Again, right on that edge between total, like kind of deep, but it's pretty obvious, I hope. Maybe. But now we've got this sort of vector stuff hanging out, but that's no big deal. So I get to tell you at least one more time this term, FU. Right, this is the rate of change of F in the U direction, and that's a number. And then the distance moved in the U direction is delta R, and this, I guess that's a magnitude. Okay, so that's just a number. This is how far you step. This is the steepness in the direction you just stepped. Anybody remember the formula for FU? That's a great straight line. But the math formula for FU? Gradient, yeah, involves a gradient. That's pretty nice. And then U is the direction you're moving in. Delta R is the amount you moved. So I claim that delta R is U delta R.
Wait, what happened to R in the second step?
I just didn't write it. I'll put it back. So this is the directional derivative FU at the vector R. So this should be the gradient of F at R dot
The U.
U. Yeah. So I've said in class, like when you're sort of imagining stepping along this path, doing these dot products, it's telling you your altitude gain, if you're going up or going down. I haven't really justified that algebraically until this is an algebraic justification of that. Okay, let me sort of write the consequences of this and see if I can tilt it a little bit more towards the obvious side and less towards the deep and mysterious side. Thanks. So, this is known as, sometimes, the fundamental theorem of calculus for gradients. So it's a new version of the fundamental theorem of calculus. So here's what this says. You have a line integral, and those could be sort of challenging to do unless you happen to know the vector field came from a gradient. And then it's super easy to do. You just plug in the endpoints to the gradient and subtract. And notice, by the way, that this answer depends only on the endpoints, not on any of the intermediate values. So if you decided to take a different route and ended up at Q, you would get the same answer. So that's exciting too, I think. It tells you that the answer for this type of integral is independent of the path you take from p to q. So that's maybe the mysterious thing. On the other hand, this says, suppose you and your friend are both at point P, and you decide, hey, we're going to meet at point Q, like the latitude and longitude. You have GPS devices or something. Let's meet there in 2 hours. And you each go off and you do your own thing. Maybe somebody goes hiking, somebody else sits down and does calculus homework, and then heads up and meets you reunite at point Q, and you would say, gee, we're at the same altitude. That would not be shocking at all, right? Because you're not tunneling through there. You're on the surface of the Earth. So that's sort of all this is saying, right? So that's sort of like the, gee, this is a not shocking statement at all, and or this is a deep statement about certain types of vector fields. So for the time being, as a practical matter, this gives us an alternative way of evaluating these things. So that doesn't involve this messiness. So what I want to try now is an exercise where you'll first get to practice this messiness just once more. It's coming up in the homework, it's good practice. And then you'll do an integral this way. And because it's math, you'll get the same answer, and we'll be happy. And then we'll go on to the next one. How's that? All right, so let's see how this goes. All right, so we want to do this along a curve. First thing we need to do is we need to parameterize the curve. And here I think it's much easiest to let it go from 0 to 1 because x is going from 0 to 2 while y is going from 0 to 3. So other parameterizations are possible. This feels like the natural one to me. So then r, is this, x and y, and r is a vector, and it traces out these points as t goes from 0 to 1. We're also going to need r prime. That's just the derivative of this. Derivative of 2t is 2, and so on. And then I wrote down the vector field 2x I hat plus 2y j hat. All right, so then I need to do this. And so I'm going to use this approach. So this is the vector field with x and y. And then this is the velocity, r prime. And now this is dt and not d vector r. It goes from 0 to 1. X and y, I want to evaluate x and y along this particular path. I want the field along this particular path. And so I plug in for x and y the parameterized values of x and y. That's a step that can be easy to forget. So x I replace with 2t, y I replace with 3t. And then I multiply out, and I do the dot product, and I get this. And then I get this. This is an old-fashioned Calc 2 integral. And I get 13. So that's that. So now let's try it the new way, using the fundamental theorem for gradients. So your task is to come up with a function, scalar function, a little f, whose gradient vector is this. So give that a try, a little trial and error. So now you're sort of like anti-gradienting instead of anti-differentiating. So give that a try and we'll see how it goes.
Like substitute.
So
like if you go
let me just say a little bit about these two
say if you go 0 to 1 and you just
steps of
substitute x.
So if we want to evaluate this using this, I say, all right, this is great. I've got a vector field, but I want to know, I want a function whose gradient gives me that vector field. So then we have to remember, what's the gradient? Well, the gradient is partial derivative x, I hat, partial derivative y, j hat. And so matching these, partial derivative fx has to be that, fy has to be that. So I say, all right, so, and here I wrote this out, the partial f, partial x, instead of this form. It's 2x, and blah has to be 2y. All right, let's see. So I'm looking for a function whose x derivative is 2x. What might that be?
X squared.
It's x squared. Maybe f of x, y is x squared. Oh, but I also need a function whose y derivative is 2y. Y squared. And I'm going to add them together because right, if I take the x derivative of this, the x derivative of y is 0. So we're in good shape. If I take the y derivative of this, the y derivative of x is 0. We're in good shape. So this is our old friend, the upward parabola that we started the course with. So now let's use this function to evaluate this line integral using this, and it should be delightful. So take a moment to do that and let this sink in, and then take a look at part C if you haven't already, and then we'll talk a little bit further. Okay, let me say one thing quickly before you start pondering question 2. So let's see here. Okay. So once we have the function whose gradient gives the vector field, doing a line integral like this is not a problem at all. You just plug in the endpoint, subtract plugging in the beginning point, and it turns out you get 13, which is the same 13 we got here. And that sort of seems, I mean, it's not magic, but it does kind of seem a little bit like magic. So here's a nice consequence of this way of doing line integrals. So if we have an f that's a gradient field, and our circle is closed, that's what this would mean. So I'm sorry, our curve is closed. We end up where we started from. Then Q and P are the same, and we end up with 0. So basically, what this says is that if you wander around for a while and you come back to where you started from, your altitude is the same. Again, it would be pretty weird if that wasn't the case. So that's what this does. And over here in this space, I'm going to write a series of increasingly deep and surprising things, I think. So if we have a vector field f that's a gradient of some scalar function, then we know immediately that f dot dr equals 0. Remember, this is called circulation of any loop, I guess. And so if f is gradient f, then we know immediately that it's path independent. That's what this says. And it then follows immediately from that the circulation about any loop is 0. And so these are phrased as theorems in the textbook, and there's some fine print. Basically, the gradient needs to exist everywhere, but I'm not going to write all that fine print. Okay, so give number 2 a try, and we'll talk that over in 5 or 10 minutes or so. Okay, so we're playing a game similar to the one I played over here. We have a vector field, and I'm looking for a scalar function xy whose gradient is f. So the gradient of little f is derivative of x, derivative of y. So then comparing partial f partial x has to be this, y has to be that. So those are those two equations. Then you say, all right, so I've got to figure out some function f whose x antiderivative is that and whose y antiderivative is this. No big deal, you think to yourself. The antiderivative of this with respect to x is that. With this with respect to y is that. So let's add them together like we did before, right? Does that work? And if you do that, you might notice, I mean, this term is nice. I made this term exactly to be that. So that worked. But there's an x over here, and that messes up the x derivative. I don't want this here. And if you took the y derivative of this, you'll also be led to a similar conclusion. So any idea how to get out of this mess? Retreat is the only way. So it turns out that this field does not have an F. It's not a gradient field. Not every field is a gradient field. We sort of saw that before geometrically. Here we're seeing that algebraically. And you might wonder, is there a way other than abject failure to tell that a vector field is not a gradient field? And happily the answer is yes. There's a test you can do to determine if you should even waste your time on this. So let's talk about what that test would be. Let's see. There is no such f of x. That's the way it goes. Okay. So how could we tell? I think I'm going to, let me do present sort of the general test for gradient fieldness, and then we'll apply in this specific case. So how could we no. So let's say someone hands you a vector field and it looks like that. I mean, in fact, that's just what happened. Someone handed you a vector field. And we want to know is there a n of x, y such that del f is f? If yes, then so this is just repeating to here, but I'm just using capital F1 and capital F2 instead of the particular functions. Okay, so now I'm going to do something at first blush that will not be clear why I'm doing it. I'm going to take the y derivative of this equation. Just humor me. I can do it, right? Why not? So if I take the y derivative, I'm going to get this. And I'm going to take the x derivative of this. Again, why not? It's a free country. So these terms on the left-hand side are mixed partials, and those are equal.
What do you mean by
Let me see. So I made this assumption. So I said, let's suppose this is true. And if you come down here and you find out that this is not true, then it must have been the case that this was not true. A couple people nodded, I was amazed. Other people looked at me weird, which is what I was expecting, because I didn't think that was I was not really happy with that sentence.
I just get a sense that it takes longer than just realizing you failed on the other one.
Oh no, it's definitely quicker. So let's, so going back to that example, I need to ask, does F1 y equal F2 x? And so then that's partial y. F1 is 2xy. And it was xy?
Yes. No.
Pretty quick.
This way.
Yeah.
So in numbers, how I thought was in the partial differentiations, the terms, is it that their partial derivative needs to be expressed in the same, if it's of x, it should be only an x, and if it's of y, it should, and not mixed? Is that
That you can.
I mean, it makes
I know what you're saying. So, let's go. Let me go back to example 1, which is going to illustrate what we're just talking about. So in example 1, we had f is 2x plus 2y. And then let's do the same thing. Partial f1 is 2x with respect to y. Does that equal the partial, let me write this thing, partial y of 2x? Does that equal partial x of 2y? Well, this is 0, and that's 0, and that's certainly something we can be sure of. So, yes. So, f is a so if all of your x terms, if all of your I terms have only x and all of your j terms have only y, then you're always going to get 0, 0, and you're always going to be in good shape. However, but if the x's and y's get mixed up, as happened here, you might get in trouble, as happened here, but you're not guaranteed to get in trouble. You could mix x and y in just a special way that it still turns out to be okay. But in general, that won't be the case, but not always. Okay, so let's see. Let me write one more thing on this board, and then we'll do a little bit more practice and wrap it up. So, actually, why don't we practice now? So try problem. Okay, so the answer to problem 2 is you can't find such a scalar, and so let's not. So if you wanted to do that, you would have to do the integral by parameterizing the curve, and that would be no fun, so we won't do that. The main point of this was to realize that you can't always find a gradient field. Even relatively innocent-looking vector fields might not have a gradient. So give problem 3 a try. You'll just be using this diagnostic test, and then we'll conclude, and I'll introduce a little bit more vocabulary. So for all of these, we're doing this test. Take the y derivative of the x component and the x derivative of the y component. And let's see. It looks to me like this one That's gonna be no. This one, yes, 0 equals 0. This one is yes.
Wouldn't it be minus y?
Wait, Dave, what?
Yeah,
Yeah.
it would be 1 and minus.
Yeah, there's minus y.
But it's still 0 equals 0.
Dave, for 6, the problem is negative 4x, not y. That one down. Wait, so you didn't,
I didn't do 4. 4 is true.
Okay.
4 is yes.
okay,
Sorry,
cool.
yep.
I didn't know. Thanks, Dave.
So this is what do we got here?
Yeah.
Because this is a 0 and that's a 0. And this one should also be yes. So this is an example of the thing Portia was asking about. It is possible sometimes to have x and y mixed together, but if they're balanced just so, you can still get something that satisfies this. So let me collect a few ideas and introduce a little bit more vocabulary and conclude. So, all right, let's see. So this quantity, partial f1 partial y minus partial f2 partial x is known as the scalar curl. And we've just seen that if curl f equals 0, then f plus f equals 0.
Is that a minus or a?
That's a minus.
That's a minus.
Yeah. So typically, rather than writing it this way, one pushes them both to the left-hand side, calls the difference of those two things the scalar curl, and says if the curl is 0, then we know that's a test. If the curl is 0, then, which means these two things are equal, then we have a gradient field.
Why? It's curl.
Great question. Why is it curl? Well, let's see. What do we know about a gradient field? Well, if we know it's a gradient field, all these nice things happen every time. With a gradient field, it's path independent. And that means that the circulation about any loop is 0. And so this means you have a vector field, and any path you take and you loop back around you get 0. So there's no circulation about any loop. And so that's the connection, and I'll say more about this next time, but that's the connection between circulation and curl. Another way about thinking of this, so now think instead of a gradient field, so imagine curl is not 0. So we know it's not a gradient field, so I can't think in terms of altitude. So let's think in terms of water flowing, or wind thing. And so it would be possible in a system like this to walk in a circle and always have the wind at your back. That would be a nice situation. That would mean that you were sort of in a whirlpool or something, or in a tornado. That maybe wouldn't be so nice, but at least it would be easy to go in circles. So that would mean there'd be some circulation, right? You can go in, you can add up all these things around a circle, and you don't have to get 0. So what we have now is a bunch of statements, all of which are equivalent, meaning if any one of these, so I'm going to say a bunch of things, and if any one of those things is true, all of the others are automatically true. And so these are statements about the vector field F on some region R where everything's defined. So if all integrals are path independent. All circulation integrals are 0. F is a gradient field. F is curl-less. No curl anywhere. This is 0 anywhere. So if you know any one of those things, all of those other things are automatically true. So this implies that, this implies that, this implies that, this implies that, and so on. So today has been a lot of algebra. I don't think I've really drawn any significant pictures. And so what I want to do next time is two things. Actually look at some vector fields and sort of talk again about what circulation means and what curl means, start to get a feel for that. And then this quantity, we'll investigate this more, and this is what Green's theorem will be. You probably have a sense like, well, maybe you have a sense, you know, like, what does this actually mean? Might this come up in other settings? How is this related to this? And so we'll see a nice relation, that's Green's theorem, and then that will be, in fact, in another fundamental theorem. So the next, well, for the rest of the course, probably every other day there'll be a new fundamental theorem of calculus. So, pretty exciting. Fasten your seatbelts. So I will be up in the dining halls for a little while if anybody has questions about homework or anything else.